add some telephone booking. And how, if I want to write on Thank you. Good day, everyone. Anyone online? I don't think there's anyone online. Okay. Because I can't even see any. Hmm? I will just because how can I start? Maybe I should allow you if it's just one person at least.
Maybe can we take it?
Maybe
we can take it.
Okay, one person at a time. So thank you. Good day, everyone. Yes, thank you. The math easier. Yes. My name is Adeshokwe Adeyemi Paul. The course secretary. So I'll be taking the last part of this course. I've taken the last part of the course. So I'll be looking at electromagnetic oscillations and alternating current, Maxwell equations, and electromagnetic wave. Can you please hear me? If you can hear me, can you please signify if you can hear me? Can you hear me? Hello? Okay, thank you. Yes. Like I said earlier, I'll be taking the last part of this course. So we'll be looking at electromagnetic oscillations and alternating current, Maxwell equations, and electromagnetic waves. Yes, before we start the class, so briefly, let me just, I don't know if you have gotten this. By now, you ought to have gotten this. So this is the tutorial booklet. Okay. So I'm going to give the first set of tutorial today. So after this class, so we'll be giving the first set. And after my session, so you'll be given the last set. So then you'll be told when to submit and the mode of submission. Okay, so please, if you have not gotten this, ensure you get it this week. Ensure you get it this week. Okay, and please kindly tell those who failed the course. So your senior colleagues that are rewriting the course, please tell them to get this as well, because your tutorial will be graded and is going to form part of the assessment, the total assessment score. So to form part of it. So today, before today's class, so you'll be given the set of tutorial questions. So let's start the class. So we want to look at electromagnetic oscillations. So just want to look at what happened when you have a charged capacitor. A charged capacitor is connected to an inductor. So we want to look at what happened. So if you have a charged capacitor and it's being connected to an inductor, the capacitor will begin to discharge through the inductor. So to begin to discharge, so it discharge. But instead of dying out, that is the electrical energy that was initially stored in the capacitor. Instead of that energy to die out, the energy will oscillate back and forth. That is between the capacitor and inductor. So the energy. So we are talking about an ideal LC circuit. Okay. So we're looking at resistance-less circuit. That is, there's no resistance. So the electrical energy that is being stored in the capacitor will be transferred to magnetic energy. So this will be stored in the inductor, and the process will just continue like that, back and forth, back and forth. So in an ideal LC circuit, so energy is never lost. So the energy is conserved. So the total energy is constant. So we have energy is never lost. So the energy is conserved. So it simply moves back and forth between the electric field of the capacitor and the magnetic field of the inductor. So the resulting oscillations of the capacitor's electric field and the inductor's magnetic field are said to be electromagnetic oscillations. So we can see this in this diagram. Okay, so let us look at the diagram here. You look at this diagram A here. We have a fully charged capacitor, and it's being connected to this inductor. So the current in the circuit is 0. So which means the total energy in this circuit is entirely electrical. So the total energy, that's the maximum energy, is entirely electrical. But as the time goes, maybe after t equals to 0, the energy stored in this capacitor will begin to reduce, that is, decrease. Okay, and at this point, so the capacitor is completely discharged. So all the electrical energy that has been stored in the capacitor has been transferred to magnetic energy. So here we now have the entirely magnetic energy. So it continues like that. Okay, continues like that. So when the pole of the capacitor, the polarity is changed, so the capacitor will begin to charge again. So here it's fully charged, and you have the total energy will be electrical. So begin to discharge again. Here the total energy is magnetic. And where we have the total energy to be magnetic, then we have the maximum current, because the current in the circuit is maximum at that point. So you can see, so back and forth, back and forth. You can have the illustration like your sinusoidal waveform like this here. So we have it something like this for capacitor. So for inductor, so the inductor, because when the capacitor, the entire energy, when it is maximum here, the magnetic energy will be 0. Here. If here is 0, the magnetic energy will be 0. The electrical energy is maximum here. So we have to be 0, something like this. So like that. So, and when the electrical energy is 0, the magnetic energy is maximum. So we just have it like that. And here, so let me use this just for this. And this thing, it takes 4 different phases, okay, to make one complete cycle. From here to here is 1/4 of the time taken to for one complete cycle, that is here. So here at this point, all the electrical energy has been converted to magnetic energy. So here is T/4. So we have T. T is the period. Period is the time taken for one complete oscillation. So here, opposite to what we have before. So here we have T/2. And back to this place, we have 3T/4. 3T/4. And here, so we're back to the starting point, so which is T. So you can see we have 4 phases, okay? So we have T/4, T/2, 3T, and T. So between here is maximum here. So here corresponds to T/4. Here corresponds to T/2. So this place corresponds to 3T/4. So we can have it like this, okay? So let's continue. So in this diagram, the diagram shows the potential difference across the capacitor, okay, in the previous circle. That's figure 1. So this is figure 2. So as a function of time. So if you look at that figure, and like what I just do, the diagram that I showed earlier. So here you have, this is, okay, so this is T/4. Here is T/2. This is 3T/4, and here is back to the initial stage. So we have ACAG. Okay, so look at ACAG. Okay, so we have it. And the figure B, so it shows a potential proportional to the current. Don't forget that we have current in the circuit. Okay, so we have this. Yes, before we continue, let me give the first attendance code. So I want to give the first attendance code. The first attendance code, BLW68. BLW68. That's the first attendance code. BLW68. BLW68. Michael Akinlolu, this is his 102 class, okay? 102, not 104. 104 we hold between 3 and 4 p.m. today. So let's continue. Now I want to look at the energy in the circuit. Energy. Okay, before we continue, no, there is no ideal LC circuit, okay? So in an actual LC circuit, the oscillation will continue indefinitely because, the oscillations will not continue indefinitely because there are always some resistance present. And what it does, it will drain the energy from the electromagnetic energy. It will drain it, okay? And it will change it to heat energy, thermal energy. So energy will be lost through that, okay? So we can see the illustration in this diagram. This is an oscilloscope. So showing how the oscillation RC circuit actually die away. If you look at here, you see the amplitude. The amplitude is large here, but with time, it dies down. Look at it. Okay, so So let us look at the energy in the LC circuit. So from your previous classes, you were made to understand that capacitor stores energy. Okay, so it stores electrical energy. So the energy stored in the electric field of the capacitor at any time, that's instantaneous energy. Instantaneous energy. Something happened there. So we have energy stored in the electric field is given as this, Q squared over 2C. So Q is the instantaneous charge and C is the capacitance. So likewise, the energy stored in the magnetic field of the inductor. So at any time, T is given as this, Li squared over 2. So I is the instantaneous current and L is the inductance. So the total energy U, so present at any instant, that's instantaneous energy, is given as this. That is the sum of the energy stored in the capacitor and that of the one stored in the inductor. That is the electrical energy plus the magnetic energy. So we have this. And now we assume that we are dealing with a resistance-less circuit. That is, there's no resistance. So no energy is lost. Okay, no energy is transferred to thermal energy. And in this case, the energy remains constant with time. So it remains constant with time. So by the time you find the derivative of the energy, that's total energy with time. So you must have 0. Because when you find the derivative of a constant, you always have 0. So if you take the derivative of this, so we have with respect to time, that's the u dt. So we have it the u dt. So we're going to have something like this. Now here, if you break this u squared, du squared, if you break it into 2, you can rewrite u squared as, q squared, you can rewrite it as q times q like this. Okay, so when you take d dt of it, so you can rearrange it in a way that you have something like this, dq dt. So that is where we have this here, dq dt. Now the main reason why we don't include this again in our differentiation is because 2 is a constant and the derivative of a constant is 0. So we don't need to not count. So that's why we don't put it. Likewise, I squared, you can break I squared into 2. So you have one with this and the other one here. Now, if you recall from your previous classes, so I, the current, is equal to the Q dt and the I dt. So if I is the Q dt, so the I dt will now be I is the Q dt. Okay, so the I dt will be d dt dq dt. And this one will give you the 2q dt squared. So you have something like this, and that's why we have this. So the height dt is the 2q dt squared. So if you now substitute this in equation 4, if you put it in equation 4, so we have this. We have 1 over cq plus I the 2q dt squared, and this must be 0. So that is the equation for LC oscillation. So that is it. And we must, because this equation, so we need to solve it. So we need to solve it. And the general solution will give us the general solution for Q, because if we want to solve it, we have the parameters. We have Q, okay, here. So we need to solve for Q. We need to solve for charge. So Q, the general solution will be Q cos omega t plus phi. That's Q cos omega t plus phi. And Q is the amplitude of the charge variations. Okay? Omega is equal to 1 over root LC. So omega is the angular frequency of the electromagnetic oscillation. That is the undamped oscillation. So we have it. And phi is the phase constant. So the value of this one will be determined from the initial conditions. So the value of phi will be determined from the initial conditions. Okay. So if you take the first derivative of equation 4 here, we take the first derivative. So we have the q dt. Now the derivative of cos is minus sine. Okay. And we want to differentiate this with respect to t. So this constant, this one, I mean this variable with t. So we become the so we multiply with this, so be here, and the derivative of cos will give us minus sine. So that's why we have minus q omega sine omega t plus theta. So that's how to find the current. Current from the previous slide, you know that current is the q dt, and you know that q is q cos omega t plus phi. So by the time you differentiate it, so you have something. So if you substitute I, that's uppercase I, okay, we substitute I for, because this Q and W, they are constant, so we can just remove them and substitute with just one constant. Okay, so you can substitute I for QW. This equation 7 will now become, equation 7 will become this, that is minus I sine omega t plus phi. Now, I is the maximum current in the circuit, the maximum current in the circuit. So let us now find want to look at the electrical and magnetic energy oscillations. So from our previous slide, you know that the electrical oscillation energy is Q square over 2C. And the solution for that equation is Q is equal to uppercase Q cos omega t plus phi. So if you take the square of it, so you have uppercase Q squared cos squared omega t plus phi, and substitute in this equation. So we have equation 9. Likewise for magnetic energy. So if you recall from the previous slide, magnetic energy is half Li squared, and I from our previous slide is minus Q omega sine omega t plus phi. So if you take the square of it, when you take the square of it, okay, the square will negate that negative sign. So we now have half L, this L, and I squared. So all these parameters for I squared, that is omega squared, Q squared, sine squared, omega t plus phi. Okay, so if you now want to find the total energy, don't forget that omega is 1 over root LC. So if you substitute 1 over root LC for omega here, so we have omega squared will be 1 over LC. So if you multiply with half L, okay, so it will be 1 over LC. So this cancel this. So you'll be left with half, that's 1 over 2C. Okay, but this one still retain, that's Q squared. Okay, so we now have this equation now leads to this. That's the magnetic energy is equal to Q square over 2C sine square D. So we now want to find the total energy. The total energy will now be total energy U is equal to U sub B plus U sub E. So it's equal to Q squared over 2C sine squared omega T plus phi plus Q squared over 2C cos squared omega T plus phi. So if you factor out the common factor, which is Q squared over 2C, so you have sine squared omega T plus phi plus cos squared omega T plus phi. Now from trig identities, sine squared theta plus cos squared theta is equal to 1. So which means sine square omega T plus phi plus cos squared omega T plus phi will be 1. So when we multiply 1 with Q square over 2C, so the total energy in that circuit will be Q squared over 2C. So we can see the diagram. So this is the diagram. Okay. So the maximum energy, that's maximum electrical energy, is Q square over 2C, and the maximum magnetic energy is Q square over 2C. And the total energy also is Q square over 2C. And the main reason why we have this is because when UB is maximum, UE will be 0. Okay? And when UE is maximum, UB will be 0. So Q square over 2C plus 0, or 0 plus Q squared over 2C will give you Q square over 2C. So note this, okay? The maximum value of electrical and magnetic energy are both Q square over 2C. At any instant, the sum of electrical and magnetic is equal to Q square over 2C. So this is constant. So when E is maximum, UB is 0. Okay? So that's that about that. Now let us look at the second. Let me give the second attendance code. This second, before we continue the class. So let's kindly take the second attendance code. Now the second code is QF P9D. QFP9D. So that's the second code. That's the second code. QFP9D. QFP9D. Yeah, thank you, Kolapo Bamishaye. So someone said the attendance coach, that page is not working. Okay, thank you. So let's continue with the class, please. The next phase is, so we want to look at damped oscillations in an RLC circuit. RLC circuit. So a circuit containing resistance, inductance, and capacitance is called an RLC circuit. So as you can see in this figure, this is inductance, the resistance, and the capacitor. So it's a capacitor, resistor, and inductor. So with the presence of this resistance, so the electromagnetic energy, because resistor will not store electromagnetic energy, so the resistor will not store it. Okay, so what it does, it release it as a thermal energy. So it releases it as a thermal energy. Okay, so because of that, the total energy in the circuit, will not be conserved, because some of energy will be lost as through heat. Okay, some of the energy will be converted to thermal energy. So unlike when we have an ideal LC circuit, so in this case, the energy decreases with time. It decreases with time, like we have in that diagram. That's this figure 3. So with time, the energy decreases. Okay, decreases. Look at it. You look at the amplitude of the current, the potential difference, even charge will decrease and eventually die out. So because of this loss of energy, the oscillation of charge, current, and potential difference continuously decrease in amplitude, and the oscillation are said to be damped. That is, the oscillation will die out. To die out. Okay, so we now want to look at the total energy in an RLC circuit, but the total energy is still UE plus UB. So we have Q square over 2C plus, but the energy is not conserved, so it is not constant. So when you take the derivative of the energy with respect to time, so at a particular time, so we have this minus I squared R, and I the eraser. So we have minus I. The negative sign indicates that the energy is being lost. Okay, so when we differentiate this, what we did before, okay, so just differentiate it. So we now have this, but instead of having 0, so we now have minus I squared R. So if we make this substitution, that is I for the Q dt and the 2Q dt squared for di dt. So we obtain this. So we obtain this and rearrange it. So when we rearrange it, we obtain this equation. The equation for RLC circuit, and the general solution for the charge is Q is equal to QE raised to power minus RT over 2L cos omega prime T plus phi. Now, omega prime is the come in, please. God forbid. Omega pi is the angular frequency of the damped oscillation. Omega pi is the angular frequency of the damped oscillation. So, and we can relate it with the angular frequency of the undamped oscillation. That is when we have an ideal LC circuit. Is the relation, okay? Omega pi is equal to root omega square minus r over 2L raised to power 2. And don't forget that omega is 1 over LC. So we now have the exponentially decaying amplitude to be Q, that is this aspect of it, QE raised to power minus 2T over 2L. And the total electromagnetic energy of the circuit as a function of time is given as this. It's giving us this. So let us look at some questions. Okay, I have about 3 questions. So we're going to look at the question briefly. So if time permits, so we can continue with the class. So the question. So briefly, I'll give you like 1 minute. I give you like 1 minute, okay, to provide the solution for the question. Please, can you all see the question? Indicate if you can see the question, please. Indicate if you can see the question. Hello? Okay, thank you. Freedom. So you have 1 minute, okay? So we want to look at the total energy in the circuit and also the maximum current. So briefly, please. So what's the total energy in the circuit? You don't know the parameter. So this is an inductor, it's a capacitor, and you have the charge. It's not missing. Look at it. It's 3.6. So an oscillating LC circuit consists of a 5.0 millihenry inductor and a 3.60 microfarad capacitor. If the maximum charge on the capacitor is 2.90 microcoulomb, what are the total energy in the circuit? Okay. Thank you, Prof. Prof. K. Maths. Prof. K. Maths. That's the total energy. So you got 1.17 microjoules. You got it. Now let's quickly look at it together. Okay. Now we have this L solution. L is 75.0 times 10 raised to power minus 3. C is 3.60 times 10 raised to power minus 6 F, and Q is 2.90 times 10 raised to power minus 6 C. And you have to find the total energy. The total energy, U, is equal to Q squared over 2C. So if you insert these parameters, that is 2.90 times 10 raised to power minus 6 here, and C 3.0 times 10 raised to power minus 6 here, so you get 1.17 times 10 raised to power minus 6 joules. That's the first one, A. The second one, B, you have to find the maximum current. Okay, now you know that the total current, total energy in the circuit is constant. Okay, and at any instant is equal to Q square over 2C. So you can now say that if you want to find the total maximum current, so it means all the energy has been converted to magnetic energy. So is when all the energy has been converted to magnetic energy that you have maximum current. So we have UB is equal to half Li squared. Half Li squared. And UB is equal to U and is equal to half Li squared. So we have 1.17 times 10 raised to power minus 6 is equal to half times the inductor, which is 75 times 10 raised to power minus 3. Okay. 75 times 10 raised to power minus 3 I squared. So if you make I the subject of the equation, so what you're going to do is to just multiply 1.17 times 10 raised to power 6 multiply by 2 and divide by 75 times 10 raised to power 3 and take the square root. Take the square root of the result. So if you take the square root of the result, you have 5.58 times 10 raised to power minus 3 amperes. Minus 3 amperes. So that's that about that. Okay. Now let's look at the second question. Question 2. Question 2. So the second question, say in a certain oscillating LC circuit, the total energy is converted from electrical energy in the capacitor to magnetic energy in the inductor in 1.50 microseconds. What are A, the period of oscillation, B, the frequency of oscillation, C, how long after the magnetic energy is a maximum will it be a maximum again? So let's quickly attempt this. So you have 1 minute. 1 minute. I'm waiting. Hello? Anyone? Okay, a period is 6.0 microseconds, correct? Correct. Davis Andrew, correct. What about B part? The period of oscillation. What's the period of oscillation? Okay, let's look at it together. So if you have, let's say we have the diagram, something like this. So here, all the energy here is electrical. So at this point, the energy has been converted to magnetic. And this point, we have T over 4. Here, the energy has been converted to electrical here at T over 2. Here, the energy has been converted to 3T over 4. And here, back to the initial stage. Okay? Now, the energy will reach maximum here, maximum magnetic at this point. So we have T over 4 is equal to 1.5 microseconds. So the period is equal to 6.0 microseconds. Okay? And the second one, B. So all you need to do is to just relate period and frequency. Okay, we want to find the frequency. Frequency is equal to 1 over T. So which is 1 over 6 times 10 raised to power minus 6. And this will give you 1.67 times 10 raised to power 5 Hertz. That's the second one. Okay, and the last one, C. So the energy here, it reached maximum maximum magnetic energy here and here. So all we need to do is to now find the difference between the two. That is 3T over 4 minus T over 4. And this will give you 2T over 4, which is T over 2 and is equal to 6 microseconds over 2 and is equal to 3 microseconds. So the first one is 6 microseconds, the second one is 1.67 times 10 raised to power 5, and the last one is 3 microseconds. Okay, now let's look at the last question. Now, before we take the last question, let me take the last attendance code. The last attendance code. Okay, so I don't need to take it. Okay. So I'm just being told that the form doesn't accept the acceptance, the attendance. So probably next class, okay? But that doesn't mean that you shouldn't, that should not come for the next class, because I know majority of you wouldn't want to come because you know that they wouldn't, maybe since the attendance platform is malfunctioning, that will not take attendance. And the main reason why the main reason why you usually attend is because of the attendance. So please, you have to come, because let me just say this, your test result is out. Your test result is out, and there are some people that they perform exceptionally well. Like we have someone that had 20/20, but at the same time, you see how some that didn't do well at all, like even more than 50%, scored less than 10. So we even have as low as 1/20. We have as low as 1/20. And I discovered that those people that are scoring like below average are those that don't usually come for the classes. So I don't know why. So if you don't come, there's no way you can understand. So you have to come if you know that you want to do well and you want to pass this course. Okay? Don't come because you know that we're going to take the attendance. Come because you know that you want to gain something. I pray that God will help you. Now let's look at the last question. Let's look at the last question. In an oscillating LC circuit with C equals 64.0 microfarad, the current is given by I is equal to 1.60 sine open bracket 2500t plus 0.680. You close the bracket, where t is in seconds, I in amperes, and the phase constant in radians. How soon after t equals 0 will the current reach its maximum value? That's the first question. The second question, what are the inductance and the total energy? What are the inductance and the total energy? So let me just give you the answer. So please, when you try and solve this and compare your solution with the given answers. That's A. The answer is 3.56 times 10 raised to power minus 4 seconds. B, the answer is, that's L is equal to, so this one is T is equal to, L is equal to 2.50 millihenry, and C is equal to 3, and that's the total energy. U is equal to 3.2 times 10 raised to power minus 3 joules. Yes. So now let us look at the first tutorial set questions for this course. The first tutorial set question for this course. Are you there, please? Indicate if you are still there. indicate if you are still there. Okay, thank you, Oluwakemi. Now, the first tutorial set. If you have not gotten this, please ensure you get it, please. Okay, PHY 102 tutorial booklet. So tutorial set and workbook. Okay, so chapter 1, question 1. Chapter 1, question 1. Chapter 1, question 1. Question 5. Question 5 and question 10. And question 10. Chapter 2. Question 1. Question 3. 6 and 9. Chapter 3. Question 1, 6 and 10. Chapter 1, question 1, question 5 and 10. Chapter 2, question 1, question 3, 6 and 9. Chapter 3, question 1, question 6 and 10. Thank you for your time. So we'll meet next Friday by 9 a.m. Thank you.
Good afternoon, students. I'm happy to be here today. I want to believe that in the last class that you had, you went through disagreement. And now I want to assume that you understand what a disagreement is and the types of disagreement that we have. I mean, just as a quick recap, I want to let you know that we have factual disagreement, we have verbal disagreement, we have evaluative disagreement, and we have interpretative disagreement. Under evaluative disagreement, as you should have known by now, we have evaluative vertical disagreement, evaluative aesthetic disagreement, and evaluative pragmatic disagreement. I just want you to note that. But today, we want to go to argument. And the first point that I want you to note is the question, how does argument arise? I want to make a bold statement here this afternoon to let you know that argument does not arise unless there is a disagreement. In other words, disagreement gives birth to argument. If there is no disagreement, then there can be no argument. Are you following that? For instance, now look at it. If Jingo says OAU is in Ile-Ife and Bongo says OAU is in Osun State, do they disagree? You will agree with me that there is no disagreement. If there is no disagreement, then there is no need to argue. Do you get that? Because in this case, in this example that we have here, both speakers can be correct. And when you have a case when both speakers can be correct on an issue, then there is no disagreement and there can be no argument. Do you get it? Look, argument in most cases ensues just in case that you need or intend to convince your audience about the plausibility of your position. Is that clear? When you say something and you have an opponent or someone, a friend, who says, no, I disagree with you, that is when you need to provide an argument to justify that your position, to defend that your position. Is that clear? So we are going now because oftentimes there is a misconception about argument. Oftentimes, I let you know today that what we think is an argument is actually not. I mean, for instance, now in your hostels, in cafes, when you are watching football, in departmental foyers, you are standing there with your friends or colleagues, and then an issue comes up. Before you know it, you all begin to ventilate and then to shout, make a noise. And once that kind of a noise goes around, people hear it, they say there's the assumption that, oh, they're arguing there. Or if in your room, you are just making a noise and all of that. Somebody say, oh, in that room, they're arguing. It happened to me when I was in Angola in those years. But I want you to know that argument, shouting, making a noise is not synonymous with arguing. You know, actually, I mean, these days, I tend to let students know that argument actually does not make a noise. Once you begin to make a noise, something is wrong. It's actually not argument. Because, I mean, especially one thing that argument needs is people who are going to listen. When 2, 3 people can be talking at the same time and your noise will will disturb people around, that is not argument. Are you following that? Now, what is an argument? What is an argument? An argument consists of a group of statements. I want to let you know that, and I think you should note that point. An argument consists of a group of statements. Among this group of statements, one of them is the claim, which you also want to refer to as the conclusion of the argument. You get that? And the rest of the statements are the premises. Okay? I want to give you an example here, just to put those things together that I've just mentioned. I will not attend field 102 class today. This is because my body is weak. Here, you want to ask, which one is the claim and which one is the premise? Here, we want to say that the statement, I will not attend field 102 class today, is your claim. The reason you give to support that your claim is your premise. And what is the premise here, or what is your reason here? Is that your body is weak. Is that clear? So I want you to get that. That is a simple example of what an argument is. And let me quickly make it clear here. A claim or a conclusion is the position that you as an arguer or any arguer is intending to convince his audience about. That is your claim. That is the position you want your audience to accept or agree with you upon. Is that clear? The premises or your reasons that you have provided, they are facts or evidences that you want to use to support the claim. Isn't that? So how strong your evidences or premises or reasons are determines how strong that your argument is going to be. Is that clear? So basically, in logical reasoning, there are two types of reasoning. In logical reasoning, basically, there are two types of reasoning. We have deductive reasoning and we have inductive reasoning. And I want you to know that reasoning produces argument. Argument is therefore like a byproduct of reasoning. Hence, we also have two types of arguments. And what are those? You have the deductive argument and you also have the inductive argument. I go again. You have the deductive argument and you also have the inductive argument. Is that clear? Do you get it to that point? How many types of argument do we have? We have deductive argument and we have inductive argument. How many types of reasoning do we have? We have deductive reasoning and we also have inductive reasoning. Now you have just been told now that argument is a product of reasoning, and you have to master and take note of that point as we go on. Now let us pick the first type of argument. The first type of argument there is a deductive argument. What is a deductive argument? A deductive argument can be understood in one or two or three ways. One is a deductive argument is an argument in which the premises purport to provide a conclusive support to the claim. Is that clear? Did you get that? No, a deductive argument is one in which the premises purports to provide a conclusive support to the claim. It can also be an argument in which the premises purports to guarantee the claim, or an argument where the premises purports to provide a guaranteed support to the claim. Is that clear? So it's also where there seems or appears to be a relationship of necessity between the premises and the conclusion. You get that? That we are talking about deductive argument, and we are going to get that. We are going to be clear about that as we go on. So there is something that you now need to understand about what we have just said. When you note the term purports, seems, or appears, isn't that? When the premises purports to provide a conclusive or guaranteed support, or when the premises seems or appears to provide a relationship of necessity, take note of those terms. So now, when the premises in fact provide a conclusive or guaranteed support to the claim, then the deductive argument is valid. Otherwise, invalid. Okay? So let's have examples of that. Consider the following examples. All men are human, that is premise 1. All human are mortal, that is premise 2. Therefore, our claim, all men are mortal. In this argument, there is a relationship between the premises and the conclusion. And if you look at it well, do you want to say that in this argument, the premises actually provide a conclusive support to the claim, or they do not? Don't forget what we said about a deductive argument. We said a deductive argument is one in which the premises purports, or in which it seems that there is a relationship of necessity between the premises and the claim. And consider this example that we have here. All men are mortal. All men are human. All human are mortal. Therefore, all men are mortal. Let's pick it this way, because you have to understand the procedure that is guiding the deductive reasoning. The point is this: let us assume that the statement all men are human is true, and we also assume that the statement all human are mortal is true. If we assume that those two statements are true, is it possible for the statement all men are mortal to be false? So you find out that in this case, if it is true that all men are human is true, and all human are mortal is true, it is impossible for the statement all men are mortal to be true, because you have this example as an example of a deductive argument where the premises provide that kind of a conclusive support to the claim. And what it means is this: this example is an example of a deductive argument that is valid. I want you also to take note of something. Take note that if you watch the two premises very well, you are going to observe that what the statement that is in the claim is already contained in the statement of the two premises. Do you get it? So a deductive argument is actually an argument where the premises implicitly contains the conclusion. The premises implicitly contains the conclusion. Let's go to the second argument. So the second example, look at it. Mr. Jingo, that is premise one. Mr. Jingo is either a lawyer or a doctor. Premise two, Mr. Jingo is not a lawyer. What follows? Therefore, Mr. Jingo is a doctor. Look at that premise one. Mr. Jingo is either a lawyer or a doctor. Let us assume that is true. And if it is true that Mr. Jingo is not a lawyer, what follows? You find out that Mr. Jingo is a doctor is what logically what follows. Do you get it? That again gives us an example where you have a relationship of necessity between the premises and then the claim, in which case the claim again is implicitly contained in the premises of the argument. Consider other examples that we have here, that is to let you understand the point that we are making. But take note of these other examples. One, premise one, all men are male. All male are dog, that is premise two. Therefore, all men are dogs. Isn't that interesting? But take note of that argument. Let's get to the next one. All ladies are female. All female are goats. Therefore, all ladies are goats. Isn't that? If you are the emotional type, you say, no, this can be a wrong argument. Why? Because why will he say that all men are dogs or all female are goats? We are actually, when you talk about deductive argument and its validity, as we are coming to learn, when we get to validity or invalidity, you find out that whether the statement in the argument, in the premises or conclusion are true or false does not affect the validity or invalidity of the argument. Is that clear? So take note of these examples as we move forward. Let us now go on to what we are going to classify as validity or invalidity of deductive argument. Are you there? Again, I want you to note the use of purports, use of seems, use of appears in the definition of a deductive argument. Okay, is the one where the premises purports or seems or appears to provide a guaranteed or conclusive support to the claim, or the one in which the relationship between the premises and the claim appears to be that relationship of necessity. When in fact, and I want you to take note of that, when in fact the premises provide a conclusive or guaranteed support to the claim, the deductive argument is valid. Otherwise, it is not valid. Is that clear? And I want you to take note that not every conclusion follows from the premises. Not every conclusion. When the conclusion does not follow logically from the premises, as you have been told, the argument becomes invalid. Is that clear? A deductive argument is valid and only if it is impossible for the conclusion of the argument to be false, given that the premises are true, then it is valid. That is, when you have a deductive argument in which it is impossible for the conclusion of the argument to be false, given that the statements in the premises are true, then you have an argument that is valid. Okay? But otherwise, when the conclusion fails to follow from the premises, then what you have is a deductively invalid argument. Do you get it? But there is something that I want you to take note at this point. That is the point that you have, that the last point on that slide. It then follows that deductive argument can be either valid or what? Or invalid. If it follows that deductive argument can be either valid or invalid. That is not all you are. The question that you might be asking now is, okay, what are the conditions that are going to make a deductive argument valid? Let us go on to see that. Now consider this one. All lizards are reptiles. All lizards are animals. Therefore, all animals are reptiles. You find out that this argument as it stands is invalid. Is invalid. You know, don't forget that we are not dealing with whether or not the statement in the argument is true or the statement is false. We are going on to understand what can make an argument, a deductive argument, either valid or invalid. Look at the next example. All dogs are snakes. All snakes are cockroach. Therefore, all dogs are cockroach. You'll be surprised that this argument is valid. Isn't that? Maybe you are saying, why is that invalid and why would this become valid? Let's go on. I mean, take note of these examples also. All men are monkeys, all monkeys are birds, therefore all men are birds. It's going to be valid. Don't forget that we are talking about reasoning here, not about whether those two the statements in the argument, whether they are valid, whether they are true or false. We are talking about reasoning. Reasoning follows a process. Once your reasoning does not follow a valid process, it does not matter how validly looking the argument is, it is going to be valid. Did you get what I just said? I said reasoning has a process, and valid reasoning has a process. Once your argument or reasoning does not follow a valid process, it doesn't matter how good looking that argument may be, it is going to be invalid. Do you get it? So this one that we have here, all men are monkeys, all monkeys are birds, therefore men are birds, is a valid reasoning. That is, suppose that premise 1 is true, suppose again that premise 2 is true. Therefore, you cannot reject that conclusion as the conclusion if you can grant that each of those two premises are true. Is that clear? Look at the next one. All men are animals, all animals are goats, therefore all animals are men. That is obviously going to be invalid. Okay, so there is a point that you need to understand about deductive argument and validity. There is a point you need to understand, and that is to let you know that there are misconceptions about validity of a deductive argument. Did you get my point now? There are some misconceptions about the validity of a deductive argument. Let us look at the first one. That is, there's a misconception which associates validity with truth. There is that misconception which we argue that, look, a deductive argument can only be valid when the statements in the argument are true. But given some of the examples that I've presented thus far and that I've described them as valid, you should at least have observed that at least one of the statements there may not be true. So that is to tell us that the fact that a deductive argument is valid does not mean that the statements are factual or true. In other words, you could have a deductive argument that is valid even when all or some of the statements are false. You get it? You could have a deductive argument to be valid even when all or some of the statements of the argument are false. You get it? Now, I want you to note a point here. That is why it is I put note there. Validity of a deductive argument does not depend on the fact or truth of the statement. Validity of a deductive argument depends on the structure of the argument. Did you get that? It is my wish that you note that point, that validity of a deductive argument does not depend on whether the statement in the argument is a fact or whether the statement is true. Validity of a deductive argument depends upon the structure of the argument, the logical structure. The logical structure of the argument. Is that clear? Now, there are many valid structures for a deductive argument, but I want to give you one or two that appear to be common ones, which you may just quickly memorize and then use them. The first one that you have here is all F are G. Premise 2, all G are age. Therefore, all F are age. F stands as a variable, isn't that? G stands as another variable. We have three of them there, and age. It then means that here, if you supply terms for those symbols, you are going to have an argument. And the argument that you're going to have when you supply terms here appropriately, you are going to have a deductive argument that is going to be valid. That is what it means. Do you get it? So it's not if I supply terms here and then the statement is false or whatever, it doesn't matter. You could have a deductive argument that is valid and all the statements are false. When you say that all lions are goats and all goats are dogs, therefore all lions are dogs, that is a valid argument, even though all the statements there are not true. Do you get it? So you are going to take note that validity is not about the truth or falsity of the statement that you have in the argument. It is about the structure of the argument, the logical structure of the argument. Validity is determined by the logical structure of the argument, not about whether the statements in the argument are true or false. We are coming to the issue of the statement. But when you talk about validity, there is an argument, a deductive argument can only be valid when it follows a valid structure of reasoning. Is that clear? I think that is that point is well made. Another valid structure that you may have that is common is some F are G and some G are H, and therefore some F are H. Now, I've told you there are many valid structures as you have so many invalid structures. And that is to tell you that you have to double check your argument whenever it is a deductive argument to ensure that it follows a valid structure of a deductive reasoning. Is that clear? Wrong assumption number two. Wrong assumption number two. It is also wrongly assumed that deductive argument can only move from a general premise to specific premise or claim. For instance, you have all footballers are professionals. Mikel Obi is a footballer, therefore Mikel Obi is a professional. Yeah, this may be one of the valid arguments that is deductive that you have, but the assumption that a valid argument can only, a valid deductive argument can only move from general premise to specific premise or a claim is not correct. As you have it in the example, deductive argument can move from general premises to particular claims. It can also move from particular claims to particular premises to particular claims. What happens is the structure of the argument. The deductive argument is not just a box to the corner that it can only move from one general premises to particular premises or particular claim. No, it can move either way. Or what matters is the structure of the argument that you are presenting. Once your argument is a deductive argument, then you could have it move from particular premises to a particular claim. You can also move from general premises to general claim. Isn't that? Look at it. All men are mortal. Let us say all men are human. That is P1. All men are human. All human are mortal. Therefore, all men are mortal. All the statements that you have there, they are general statements. Isn't that? Moving from general premises to general conclusion, general claim, as it were. Is that clear? All right. Now, wrong assumption number three. It is also wrongly assumed that deductive argument with false premise necessarily have a false conclusion and then it is invalid. That assumption is a widespread one, actually. It appears to be the case that once you have a deductive argument to have a false premise, then you must have a false claim. And once you can have a false premise and false conclusion, then it is an invalid argument. That is also not correct. That assumption is not correct. As we have said it, what makes a deductive argument valid is not whether the statements there are false or are true. Okay? A deductive argument valid is the structure of that argument. Don't forget that. I mean, you are going to use some terms and then you relate those terms with some other terms. Look at it now. In P1 of this example, all lions. Look at the word are. We use that one to relate that lions to reptiles. We say all lions are reptiles. All reptiles are mammals. Therefore, all lions are mammals. I want you to note the recurrence of that verb, nominous verb, are there. You can see that it appears in each of the statements. So ensure that when you want to present your argument, you maintain a consistency in that presentation. Otherwise, your argument is going to look focused and it's going to tear apart. Do you get it? All lions are reptiles. All reptiles are mammals. Therefore, all lions are mammals. Though this argument has false premise, but a true conclusion, it is still a valid argument. Is that clear? That is to show you that this assumption that once a deductive argument possesses a false premise or a false statement, it is invalid, is not true. Do you get it? A deductive argument may have all or some of its premises to be false and still be valid. It all depends on the structure of the argument. There are so many examples that you can use to prove that. You could have a deductive argument that is valid with at least one statement to be false, or with at least one statement to be true. It can still be valid. Don't forget, validity is about the structure of the argument. And as well, you could have an argument where all your statements in that deductive argument are true, and that deductive argument is still going to be false. Do you get it? I can quickly give you an example here. You can say all men are human. All women are human. Therefore, all women are female. That is going to be invalid. You get, though it may pass as an example of a deductive argument. Okay, but it's going to be invalid. It's going to be invalid. So you could have an argument, a deductive argument, with all the statements false, that is valid. You can have a deductive argument that have all the statements true, and then it is invalid. It all depends on the structure of that argument. Is that clear? All right. I want to know, I don't know if you have a question. Maybe there may be a means to accommodate that eventually, but try to note those points that I'm trying to make. They are very clear points, and you must note them regarding deductive argument. Now, let us now bring together features of a deductive argument. We have now noted that only deductive argument can be one, either valid or invalid. Is that clear? Deductive argument can be either valid or invalid. Do you get that? Again, deductive argument can be either sound or unsound. Do you get it? Deductive argument can be either sound or unsound. Now, we have talked about validity, and you remember that we've mentioned that what determines validity is the structure of the argument, isn't that? Yeah. What about soundness or unsoundness of a deductive argument? We're going to get that, but you should also remember that one of the things that deductive argument cannot be is that it cannot be either weak or strong. Weakness or strength is they are not part of the conditions or features of deductive argument. What you have when you are talking about a deductive argument is you ask, is this argument valid or is this argument invalid? That is it. Or again, you may ask, is this argument sound or is this argument unsound? Is that clear? Those are the features of a deductive argument. Now let's move on and see features of soundness and sound and unsound deductive argument. Sound and unsound deductive argument. I hope you are there listening to me. Now, as I've said it, apart from being either valid or invalid, another feature of a deductive argument is that it can be either sound or unsound. Now, what is it that can make a deductive argument to be sound? When can we say that a deductive argument is sound? We have known now that what makes a deductive argument valid is the structure of the argument. And I have tried to present to you at least two of those structures that are valid, isn't that? So what is it now that can make a deductive argument sound or unsound? Let us now move forward. For a deductive argument to be either sound or unsound, there are two conditions to be noted. Okay? Those two conditions are: one, validity. Is that clear? The second condition is truth. Is that clear? That is, there is no deductive argument that can be sound if those two conditions do not hold. In other words, for a deductive argument to be sound, one, it must be valid. Two, the statements of the argument must be true. Hello? One, for a deductive argument to be sound, it must be valid. And the statements in the argument, they all have to be true. Is that clear? So for instance, look at it: validity and truth. Validity and truth. Those are the conditions for soundness. And I put it there, said V, it means that V plus T equals S. Are you there? V plus T equals S. And it also follows that V minus T equals not S. It also follows that T minus V equals not S. Then let's explain that one again. We said validity and truth determines soundness. That is, for a deductive argument to be sound, two conditions must hold. One, the deductive argument must be valid, and all the statements in that argument must be true. Is that clear? That is the sense of V plus T equals S. Validity plus truth equals soundness. Is that clear? Look at it. They said, supposing you have a valid argument, but at least one of the statements in that argument is not true, it follows that that deductive argument is not sound. Is that clear? V minus T, validity minus truth equals not sound. Is that clear? validity minus truth equals not sound. Okay, so the other one that we have, truth minus validity, again equals not sound. In other words, if you have an argument, a deductive argument, where all the statements in the argument are true, but the argument is not valid, it cannot be sound. Is that clear? Look at it, for instance. Once an argument is invalid, it cannot be sound. Is that clear? Once an argument is invalid, it cannot be sound, whether or not the statements there are true. Once there is one of those two conditions that does not hold, then a deductive argument cannot be sound. Is that clear? A deductive argument cannot be sound. Okay? An invalid argument is automatically unsound. Are you there? An invalid argument is automatically unsound. And what we are saying is that only a valid argument can be sound. Only a valid argument. Only a valid argument can be sound. Once an argument is invalid, it cannot be sound. Is that clear? So I want you to note something there, because oftentimes we use those terms, valid, sound, argument, without being clear about what they mean. An argument cannot just be sound. Is that clear? And I want you to note here again that a validity, invalidity, soundness, or unsoundness, those are features or qualities of a deductive argument, not of any argument, just any argument. Not all the arguments are deductive arguments. There are arguments that are not deductive. An argument that is not deductive can neither be valid or invalid. An argument that is not deductive can neither be sound nor unsound. Is that clear? So you have to, before you use the term validity or invalidity, before you use the term soundness or unsoundness, you have to determine, is the argument in question a deductive argument? Is the argument in question a deductive argument? Once it is not, you are not going to apply the term valid or invalid. You are not going to apply the term sound or unsound. I hope you are clear about that now. So the first thing you have to do is, when you want to go on the process of reasoning to present arguments, you have to determine, which argument am I presenting? Is it a deductive argument? It is only when you are presenting a deductive argument that you are going to then apply the term, you are going to decide or determine or judge that argument whether it is valid or invalid. It is then that you're going to judge that argument whether it is sound or unsound. Exactly. I'm dwelling on that so that from today you are going to go back and minimize or be careful apply those terms. It's so often I mean, it is a widespread. Don't you get that my valid reasoning? Oh, that argument is not sound. No, your reasoning is not sound. You don't throw those terms around without first ascertaining whether the reasoning in question is deductive reasoning. Once it is not a deductive reasoning, the terms validity and soundness, invalidity or unsoundness, they do not apply and cannot be used. Is that clear? So a deductive argument is unsound when at least one statement is false. Once you have a valid argument and one statement of that argument is false, that argument again becomes unsound, even though if the argument is valid. Can you see the strength of the two conditions that determine soundness? It means that, one, if your argument is invalid, it cannot be sound. Is that clear? Did you know that now? Again, it means that once at least a statement of that your argument is not true, that your argument can again not be sound. That is the strength, that is the significance of deductive argument and whether it is sound or unsound. Is that clear? Don't forget, we talk about validity. That validity is determined by the structure of the argument, not about whether the statement of the argument is that true or false. You can see now, at this point, you can see that when you want to determine the validity of an argument, of a deductive argument, you are not concerned here with whether the statement is true or false. The statement might be true and the argument is going to be valid. One of the statements might be true, one of the premises might be true, and you are still going to have a deductive argument. Okay? None of the statements there might be true, and you are still going to have a deductively valid argument. We are talking of validity, isn't that? In other words, it means that when you are thinking about validity, truth does not play a role. Whether the statements in the argument are true or false doesn't matter. What matters is the structure of the argument, the structure of your reasoning. Once your argument follows a valid structure of reasoning, then your argument becomes valid. Is that clear? But when you come to soundness, the case becomes different. When you come to soundness, then you have to factor those two conditions into it. In other words, you have to factor in validity and you have to factor in truth. Your argument cannot be sound when it is not valid, or when it is valid, but at least one of the statements of the argument is not true. Is that clear? I think I've dwelt on that, and then you can take note of that. Another point that I want you to note is that when you talk about strength or weakness, that is not an attribute of a deductive argument. Is that clear? When you talk about strength and weakness, that is not an attribute of a deductive argument. A deductive argument can neither be strong nor weak. In position of that, a deductive argument can only be either valid or invalid. It can also only be either sound or unsound. Is that clear? Now, I want you to do something wherever you are listening to me. I want you to now first of all, construct a valid argument. Now, I've given you the formula to do that. First of all, construct a valid argument. Do that. Construct one valid argument. And after you have done that, you are also to construct one invalid argument. Is that clear? Then go on to construct at least one sound argument. one sound argument. One sound. Now let's now give an example of a sound argument because we don't have it here. This is where the thing stops to be continued. Now, I want you to know that, listen to this one. Premise one. If you say that all women are human, all women are human, and you say that is premise one. Premise two, all human are mortal. All human are mortal. What's the conclusion that will follow that? Therefore, all women are mortal. You want to judge. One, is that argument valid? Two, is there at least one of the statements there that is false? And you want to take note that in that example, the argument is a valid argument by the structure of valid reasoning. And then each of the statements concerned there, they are not false, which means you have an example there of a sound argument. It combines the two. It is valid, and then the statements, they are true. Is that clear? Do you get that? Okay. Now, I want to quickly mention inductive argument. There's any other point I want to make on deductive argument. I'm going to make it along because of our time. I want to talk about inductive argument, and I want you to take note of that. Inductive argument as against deductive argument. Inductive argument is an argument where the premises provides a probable support to the claim. Do you get that? An inductive argument is an argument where the premises provide a probable support to the conclusion or to the claim. That clear? A probable support. It is also an argument where the premises probablify the claim. Isn't that interesting? It is an argument where the premises probablify the claim. Unlike a deductive argument where the premises provides a conclusive support to the claim, that is when the argument is valid. In the case of an inductive argument, the premises only provide a probable support to the claim. And that is why the premises only probablify the claim. Is that clear? And that is to let you know that it doesn't matter the premises. It doesn't matter the premises. There is always the conclusion is just probable. The conclusion is probable. The relationship between the premises and the conclusion of an inductive argument is not a relationship of necessity, just as you have it in the deductive argument. Do you get it? The relationship between the premises and the conclusion of an inductive argument is a relationship of probability. Is that clear? The relationship between the premises and the conclusion of an inductive argument is a relationship of probability. Okay? The given a line of premises in an inductive argument, the conclusion only follows with a degree of probability. This means, granted that the premises are true, then the conclusion is only probably or is likely to be true. Isn't that? Yeah. Now, I want you to, let's consider this example. When you say that I used paracetamol, yes, I used paracetamol on Monday, it cured my headache. I used paracetamol on Tuesday, it cured my headache. I used paracetamol today, it cured my headache. Therefore, if I use paracetamol tomorrow, it will cure my headache. Isn't that a good reasoning? It's an inductive reasoning. You are making an inference from what has happened. Isn't that? You are making an inference of what is yet to happen from what has happened. That is an inference. Okay? Now, I want you to note something at this point so that I won't miss that point. And it's also very, very important for you to take note. One, observe that when we are talking about deductive reasoning, we are saying that implicitly it is assumed that the conclusion of a deductive reasoning is implicitly contained in the premises. Can you remember that? Yeah. But look at inductive reasoning. In inductive reasoning, the conclusion of an inductive argument is outside of the premises. Can you observe that? Look at the example I just gave you now. I've used paracetamol for the past 3 days, and it has cured my malaria. Isn't that? Therefore, the next paracetamol that I will use is going to cure my malaria. You find out that the next, that information is outside of the information already provided in the premises. So the conclusion is outside of the evidences or the premises that were provided. Isn't that unlike the deductive argument, where expectedly the information provided in the conclusion is already contained in the information provided in the premises? Is that clear? Do you take note of that? Now, I want to let you have this example too. I got bread from Every Bite 35 times, and it was delicious all those times. That is premise one. My friend got from them over 100 times, and they were all delicious. Therefore, the next loaf of bread I will get from Every Bite will be delicious. Isn't that? That is an inductive reasoning. You are making an inference from the known facts. You are now assuming that the next event is going to be like that. That is you find out that the relationship between the premises and the conclusion of that argument is, unlike a deductive one, is not that of necessity. Okay? Whether the inductive argument is strong or weak, as we are going to see shortly, is a matter of the type of the type of information provided in the premises, or the relationship provided by the premises to the claim. Do you get it? So the example that you have now, you find out that there is a probability, at least howsoever small, that the conclusion might not follow. Isn't that? We are not bound by the information in the premises to accept the conclusion. Isn't that? Yeah. Look at it. We say that an inductive argument can only either be strong or weak. And let me quickly make you know that an inductive argument cannot be valid or invalid. Is that clear? An inductive argument cannot be valid or invalid. An inductive argument cannot be sound or unsound. Is that clear? The information that you have in the premises of an inductive argument is not implicitly contained in the information you have in the premises. The information you have in the conclusion of an inductive argument is not thought to be implicitly contained in the information you have within the premises. Do you get it? The conclusion of a typical inductive argument lies outside of the information provided by the premises. Is that clear? Now, what can make an inductive argument either to be strong or to be weak? An inductive argument becomes strong when the premises provide a high probable support to the claim. I come again. An inductive argument is strong when the premises provide a high probable support to the claim. And an inductive argument becomes weak when the premises provide a low probable support to the claim. Do you get it? But I've given you an example of an inductive argument. You have a lot of them around. You get it? But its own structure is different from the structure of a deductive argument. Do you get it? Moves from evidence and then infers the conclusion. Is that clear? Now, let's have an example. I give you this example and I want you to quickly determine whether this inductive argument is going to be strong or weak. Okay? It has been raining for the past 50 years in August of every year. It has been raining in August of every year for the past 50 years. Therefore, it will rain in August next year. Or since we are not yet in August of this year, you may say it will rain in August this year. It has been raining in August of every year for the past 50 years. Therefore, it will rain in August of this year. That's an inductive argument. Do you then want to judge that argument as strong or weak? Look at it and consider this one. It rained in August last year. Therefore, it will rain in August this year. Consider those two inductive arguments and decide which one you want to decide that the premises provide a high probable support to the claim. You're going to see that the first one appears to be strong compared to the second one. Isn't that? Because if indeed it is true that it has been raining in August of every year for the past 50 years, then we can strongly believe that it is going to rain in August. Yeah, isn't that? We can strongly. It's still a matter of probability. You know, everything can change. But given that premise, we have a strong evidence to accept the conclusion. Is that clear? given the premises or that premise, we have a strong evidence, strong foundation to accept the claim that it is going to be like that. But whether it is like that or not is still a matter of probability. Don't forget what we said. We said an inductive argument is one where the premises provide a probable support to the claim. In other words, it is an argument where the premises only probabilify the claim. Or you say that it is an argument where the relationship between the premises and the claim is a probable or contingent relationship. Is that clear? Is a probable or contingent relationship. Do you get it? Look at it. Consider this example again. Rain fell heavily in the month of July in the last 10 years. So it will rain heavily in June. So you find out that you could also decide is the information provided by the premise of that argument, is it strong to make, is it high? Do we have high information provided by the premise to give us a very strong argument in terms of inductive argument? Do you get it now? So I want you to know that when you talk about argument, inductive argument is not the same thing as deductive argument. Do you get it? Inductive argument will talk about, the relationship about the evidences that you already have, and then the how it strengthens, serve as a foundation for the conclusion or claim of the argument. Before I go on, I wouldn't want to forget this one. I want you to quickly note the following. One, we are talking about argument, and we are moving from premises to conclusion. Isn't that? You find out that is what we have been talking about when we are talking about the two types of reasoning. We talk about inductive reasoning and deductive reasoning. I don't want to forget, if time permits, we may come back to it next week. I want you to know that another name for premises, and I want you to take note of this one. Another name for premises, you are going to have reasons. Another name for premises is reasons. Another name for premises is grounds. Grounds. Another name for premises, you may have evidences. Do you get it? So when you talk about premises, you talk about reasons, you talk about grounds, and you talk about evidences. Do you get it? When you talk about claim, a claim is the same thing as a conclusion. A claim is the same thing as a position. A claim is the same thing as a verdict, if you like. A verdict, conclusion. Do you get it? So you move from a grounds, you move from premises, you move from reasons, you move from evidences, you move to claim, you move to conclusion, you move to your verdict, or you move to your position. Is that clear? So I have let you see that an inductive argument cannot be either valid or invalid, neither can it be sound or unsound. But when it comes to inductive argument, it can only be either strong or weak. Is that clear? So when given the premises of an inductive argument, the probability that the conclusion will follow is high, then the inductive argument is strong. Is that clear? Otherwise, when given the premises of an inductive argument and the probability that the conclusion will follow is low, then the inductive argument is weak. Is that clear? So I want you to take note, and that when given the premises of an inductive argument, the probability that the conclusion will follow is high, then we say that that inductive argument is strong. The inductive argument is not high. The inductive argument is not low. It is the premises of the inductive argument that can provide either high or low support to the claim. Is that clear? And when you have a case when the premises will provide a high probable support to the claim, you say that that inductive argument is high. When in case you have the premises providing a low probable support to the claim of an inductive argument, you say that that inductive argument is weak. Is that clear? Now look at it. I have been eating bread since Monday. I've been eating bread since Monday, and it has nourished me. Therefore, if I eat bread tomorrow, it is going to nourish me. Do you judge that the premise of that argument provides a high or low probable support to the claim? The claim is, if I eat bread tomorrow, it will nourish me. But will you think that the fact that you have eaten bread since Monday, 3 days, is enough a high probable support to judge that the inference that if you eat bread tomorrow, it will nourish you, will make that inductive argument a very strong argument? Compare to suppose that you have a 70-year-old man who says, I've been eating bread for 70 years and it has nourished me. And if I eat bread tomorrow, I believe it is going to nourish me. How are you going to judge that? You're going to find out that that second one tends to provide a high probable support to the claim, and therefore that inductive argument is more likely going to be higher than the one who just ate bread for 3 days and upon that is making a claim. Is that clear? When you say that 90% of Lagosians are 90% of Lagosians are Nigerians. Okay, 90% of Lagosians are Nigerians. And you then say that Mr. Jide is a Lagosian. Therefore, Mr. Jide is a Nigerian. Isn't that? That is an inductive argument. That's an inductive argument because we have 90% of Lagosians are Nigerians. And Mr. Jide is a Lagosian. Therefore, Mr. Jide is a Nigerian. That is an inductive argument. You only have an inductive argument that is very strong. In all probability, if 90% of Lagosians are Nigerians and Mr. Jide is a Nigerian, the probability is so high that Mr. Jide is going to be a Nigerian. It makes that inductive argument to be so strong compared to 1% of Londoners are Nigerians. 1% of Londoners are Nigerians. Mr. Kingsley is a Londoner. Therefore, Mr. Kingsley is a Nigerian. Isn't that? You find out that that is going to be that the probability that Mr. Kingsley is a Nigerian is going to be so low, and that argument is going to be weak. The conclusion that Mr. Kingsley is a Nigerian is going to be good because you have only 1%. Do you get it? Because the premise of that argument will only provide a probable support to the claim in question. Unlike the case of deductive argument, that if a deductive argument is valid, there is a relationship of necessity. It is impossible for the conclusion to be false if just in case that the premises are true. Once you accept the premises to be true and you follow a valid structure of reasoning, then to have an argument where the conclusion is implicitly contained in the statement of the premises, and then you are going to have a valid deductive argument. Is that clear? Trying to now let you see the relationship between the premises and conclusion in deductive argument and that of the argument in the inductive argument. Is that clear? Now, I also want you to know that there is something they refer to as the cogency in inductive argument. What I call it now, cogency in an inductive argument. Cogency. Cogency is the standard of success for inductive reasoning, just as soundness is for deductive reasoning. Is that clear? So, instead of asking whether an inductive argument is sound or unsound, note that we have said that that is not going to be correct. Isn't that? You cannot ask whether an inductive argument is sound or unsound. But what we have noted here is that you could then ask whether an inductive argument is cogent or not. Is that clear? Look at it. An inductive argument is cogent if and only if it is strong and all its premises are true. I want you to note that point, cogency. So, take note. An inductive argument is cogent when it is strong and all the premises are true. All the statements of the argument are true. Do you get it? Then that inductive argument is cogent. Is that clear? So take note that what soundness is to a deductive argument, cogency is to an inductive argument. I think I should make that point again to let you see. I said, what soundness is to a deductive argument is what cogency is to an inductive argument. Is that clear? Cogency is the standard of success for inductive reasoning, just as soundness is for deductive reasoning. And inductive reasoning is cogent if and only if it is strong and all its premises are true. Is that clear? So, how do we generate a formula for cogency in this at this point? Don't forget, we said S, and this for deductive argument, to be sound. Soundness means S, or S means soundness. In this case, S equals V plus T. Isn't that? S equals V plus T. Is that clear? Or V plus T equals S. Isn't that? Now let's come to inductive argument. You are going to have S plus T equals C. Is that clear? Strength plus truth equals cogent. Is that clear? So it means that if an inductive argument is going to be cogent, it has to be strong, and then the premises have to be. So it then means that you are going to have strength plus truth equals cogent in inductive argument. Is that clear? These are the two necessary conditions for a good inductive argument. Do you get it? So get this example that at least 10 million pieces of gold has been observed and they were all yellow. Therefore, gold is yellow. Can I come again? I said, that is that premise. Premise one. Since we have only one premise here, don't forget, an argument may have one premise. It's still an argument. Do you get it? But what matters is the type of relationship that your premise has provided for the conclusion. At least 10 million pieces of gold has been observed and they were all yellow. Therefore, gold is yellow. Isn't that? So what we want to test with that example is cogency. We want to be sure, one, that that argument is strong, and then the statement in the premise is true. Those are the two conditions that we need to merit to have our inductive argument to be cogent. I again want to remind you what soundness is to deductive argument, cogency is to inductive argument. The symbolic formula for soundness of a deductive argument is V plus T equals S. The symbolic formula for cogency of an inductive argument is S plus T equals C. Isn't that? Strength plus truth equals cogency. Isn't that? In other words, for you to have a cogent inductive argument, it has to be strong, and then the statements there, they have to be true. Isn't that? So the example that I've just gave you now, that is an example of an argument that is both strong and the statement in the premise is true. Then you have an argument that is cogent. Is that clear? You have an inductive argument that is cogent. Okay? So a cogent inductive argument is one that is strong and has a true premise. Okay? It provides the premise there provides good or strong probability to the conclusion. The premise provides strong probability to the conclusion. Do you get it now? Now, I want to reiterate something. before I leave that area to go to the next point that we have to talk about. Major differences between deductive and inductive argument. Major differences between deductive and inductive argument. Number one, a deductive argument is either valid or invalid, while an inductive argument is either strong or weak. Do you note that? Number two, a deductive argument is either sound or unsound, while an inductive argument is either cogent or not. Do you also take note of that? The relationship between the premises and the conclusion of a deductive argument is that of certainty, while the relationship between the premises and the conclusion of an inductive argument is that of probability. You note that as well. And four, a good deductive argument is both valid and sound, while a good inductive argument is cogent. Is that clear? You take note of that? All right. I want to let you see something. We want to move on now to elements of an argument. Elements of an argument. And there, in the elements of an argument, what we have done is to quickly address one, what an argument is; two, the types of arguments that we have, and we have noted that we have a deductive argument and an inductive argument. Now we want to go into the structure or an anatomy of an argument. You wonder what an anatomy of an argument will be? Yeah, that is the structure of an argument. When you provide your argument, there are some elements that must be in your argument. There are some elements that your argument must contain. For instance, now before you call something a soup, there are some ingredients that must be present. And just in case they are not, you say that this soup is bad, or that this is not a soup at all. Isn't that the same thing? When you talk about an argument, there are some things that must be present in that argument. When they are not present, the argument is either bad or incomplete. Is that clear? Now, there are about 6 elements that an argument consists. There are about 6 elements in an argument. 6. The first one that we have been talking about, the first two that we have been talking about, they are one, the grounds, and then the claim. Can you remember that? The grounds and then the claim. But the next 2 that I want you to also take note, they are the warrant and the backing. Hello? They are the warrant and the backing. Now this is it. You have the ground, and in the material that you have, if you don't have your own material, that is the manual. That is 102 manual. Run quickly and go and get your own. When you get to the anatomy of an argument in that manual, you are going to see the direction of the arrows there. Grounds, a line will begin from grounds and the arrow will lead to the claim. Can you see that? Is there? That is on page 116. You are going to see that 116. 116. you are going to find out that on page 116, the arrow that begins from grounds, the direction faces the cliff, isn't that? Which means that arrow is telling you the direction of the relationship. Is that clear? The direction of the relationship. It means that the grounds of premises more often than not directly relates to the claim, and the sort of relationship that the premises or the grounds have to the claim is the relationship of support. Is that clear? Relationship of what? Is the relationship of support. The grounds are provided just to support the claim, and that is what the arrow there, that is what it indicates. Okay, now you are going to see that in between that arrow, you see one arrow that points to the top, and inside the box there you have warrant. Okay, warrant. That is the third element which an argument contains. After that, you have the next arrow on top of the warrant that points to the box of the backing. Backing. Don't worry. We are going to break all of that down. We are going to explain them. Is that clear? Now, you are going to come again to that arrow between ground and claim, and you're going to see under it there are two arrows, one pointing to qualifier and the other one going in the direction of rebutter. Okay, so the picture that you have there is a picture of a complete structure of an argument. We call it a complete anatomy of an argument. You get it? Oftentimes, and listen to this one, oftentimes when you argue, we more often than not produce our grounds and our claim. And we want to explain how our grounds have provided a strong support, how our grounds have been able to justify the claim. Isn't that? But a complete argument does not end there. A complete argument does not stop there. A complete argument includes your warrants, your backing, your qualifier, and then your rebutter. Is that clear? Now, let's come back and refresh ourselves on what we have explained the grounds to be. By now, you should be able to explain to me what a ground is, other names for it, and what it does. Isn't that? We said a ground or grounds is the same thing as premises. It's the same thing as reasons. It's the same thing as evidences. Is that clear? We said grounds is the same thing as premises, is the same thing as reasons, is the same thing as evidences. Is that clear? And what function does it perform? Or if you like, what function do they perform? You want to note this one. Your argument is incomplete without grounds. Without grounds. And that is why you find out that if you make a statement, and that statement is a claim, your listeners are going to request for the grounds. Yeah. For instance, If you tell your friend this afternoon to say that I will not attend field 107 class tomorrow. I will not attend field 107 class tomorrow, and you stop. You can imagine quickly the question that your friend will ask you. What's the question? Your friend will quickly ask you why. Isn't that? Why? The question why is that you have not been able to justify that your claim. You have not been able to provide reasons for the claim. You have not been able to substantiate that your claim. You have not been able to provide premises that will support, that will strengthen, that will justify. So, grounds or premises are statements provided to justify, to support, or strengthen the claim. Premises are statements provided to justify, to strengthen, or to support the claim. Is that clear? Yeah. Yeah. Oftentimes, we should note, when we make a statement that we fail to support with our grounds or our premises, we have only made an assertion. Is that clear? We have only made an assertion. An assertion is a claim that you have not supported or justified with reasons. Is that clear? And that is why when you make an assertion, we say that you have only asserted. We expect you to justify it. Okay? It is when you provide your claim and you justify it or support it with your grounds, your premises, that at least minimally speaking, you have provided an argument. Is that clear? It is when you make a claim and you provide your reasons to support the claim that you have provided an argument. Is that clear? So I have done something now quickly. I have listed unto you the 6 elements which a complete argument contains. Isn't that? And we describe those 6 elements as the anatomy of an argument. And I have told you that you have the first one there. That is the grounds, where the arrow begins. That is your ground. The grounds, they are your reasons. They are your evidences. They are your premises. And the work they do is to justify, to support, or strengthen your claim. Is that clear? Now, can you remind me of what a claim is in an argument? If you can quickly do that, I'll be happy. Remind me what a claim does or what a claim is in an argument. Don't forget that we said a claim is what your premises intend to support. A claim is the direction. Is the direction to which the premises faces. Okay? A claim is a statement of the position that an arguer intends to convince his audience about. Can I come again on that? A claim is a statement of the position which the arguer intends intends to convince his audience about. Isn't that? Now, given this simple example that I've given you, I say that I will not attend field 107 class tomorrow. That is the position that I want you to accept. Is that clear? So that is the position that I want you to accept. And when you say why, I said that, well, I am weak, or that I want to travel tomorrow, or that I have another assignment that is more important. No, all those other statements that I'm giving you, they are my reasons to support that my one position, and I want you to accept that position from me. Do you get it? So my reasons and grounds and evidences, they are to help you to accept that my position. So that is the position that I want to convince you. That is the position I want you to accept from me. Whenever you are providing or presenting a position that you want your audience to accept from you, or that you want to convince your audience about, you are providing a claim. And we have said here that another name for that claim is a conclusion. Another name for that conclusion is your position. Another name for it, we said, it can also be a verdict. Isn't that? Yeah. Yeah. So, but I don't want you to forget that there is what we call chain argument. But I'm not sure. I don't know whether we are going to have the luxury of time to go into that even next week. The chain argument. Each statement, when you present your argument, whether you have 2 premises, 3 premises, or more than that, don't forget that each of the premises also consists of a statement, isn't that? Now, each of those statements could also be identified as a claim for which you are going to generate another set of reasons for it. That is what we do when we say that we want to construct chain argument. But this time around, we are just considering the claim and then the premises that you have adduced, you have presented to support your claim. Is that clear? Now, the next statement, the next element that I want to mention there is warrant. Warrant. What are warrants? What are warrants? I have given you, let me give you this example of the grounds and then the claim. Okay, you have it there. Nigeria is prevalent. Nigeria is prevalent of epidemics. There is prevalence of epidemics in Nigeria. That is premise 1. Premise 2, the people could not afford the high cost of health services as a result of poverty. Premise 3, the population of the poor people is more than the rich. Therefore, there should be free health care in Nigeria. Isn't that? Therefore, there should be free health care in Nigeria. You can see the premises and you can see the claim there. Okay. I want to talk about warrant. Next week, when we come to talk about the remaining elements, I also want to, I will mention to you there are some words and terms that we use to describe, or that we use to identify or to locate either grounds or claim. We call the we call the terms or words that we use to identify grounds as grounds or premise locators. There are terms or words that we use to do that. We also refer to those words or terms that we use to identify claims or conclusions as claim locators. So I'm going to quickly run through that with you next week, okay? But right now, I want you to pay attention to what a warrant is. We already have our ground and we have our claim. You are clear about that. And I want to believe that by now you should be able to provide a claim and then present your grounds or your premises or your reasons to support your claim. Is that clear? I should think that wherever you may be listening to me, you want to try that. Just think of a statement that you want your audience or your listeners to accept from you, and then think of some very clear statements that will appear in your premises or your grounds to be able to support that. We are talking about premises. What relationship does we are talking of a warrant, sorry. What relationship does warrant have to the premises and the claim? Okay, a warrant is a general statement. Listen to that. A warrant is a general statement. A warrant is a general statement, which is to connect. A warrant is a general statement which is to connect your grounds to your claim. Is that clear? A warrant is a general statement which is to connect your grounds to your claim. Is that clear? All right. Now, don't forget something, that in your premises, you are going to have particular statements. Isn't that? I am weak. I have an urgent assignment. Therefore, I will not attend field 102 class tomorrow. I am weak. Or I am weak, and again I have another urgent assignment. Therefore, I will not be able to attend field 102 class tomorrow. Those are particular statements, isn't that? Particular statements. Okay. I want you to listen to this one again. Mr. Jingo is a taxpayer, or Mr. Jingo pays tax regularly. Therefore, Mr. Jingo is eligible to vote. Or let us add one more to that premise. Mr. Jingo pays his tax regularly. Mr. Jingo, that is premise one. Premise two, Mr. Jingo is a Nigerian. Therefore, Mr. Jingo is eligible to vote. You observe again that in that box for premises, you have particular statements. Your conclusion also consists of a particular statement. Isn't that? Now, going to link or connect your is going to be a general statement that is going to serve as a connection between your grounds or premises and your claim. Isn't that? Let us deal with that example. Mr. Jingo pays his tax regularly. That is premise one. Premise two, Mr. argument. The warrant is going to go like tax regularly is eligible to vote. Can you see that? Any Nigerian who pays his tax regularly is eligible to vote, because there is a question that the warrant must answer in your argument. There is a question that the warrant must answer in your argument. When you provide your premises and to support your claim, you provide your claim, your listener may ask, why must I accept the move from your premises to your claim? What is the strength? What is the justification? What is it that is going to provide a confidence in your move from the premises to the claim? The answer to that is your warrant. And you can see in the example that we've just provided now, you find out that that is not in your in that manual. You know, it says that every Nigerian that pays his tax regularly is eligible to vote. Therefore, Mr. Jingo is a Nigerian, and Mr. Jingo pays his tax regularly. Therefore, Mr. Jingo is eligible to vote. So that warrant now strengthens the move or the connection between the premises and the claim. The warrant now strengthens it. The warrant gives confidence to the relationship between the premises and then the claim. Is that clear? So that is where we are going to stop today. I'm glad that we are able to come this far, and I want you to go over all that we have mentioned, and also in the manual that you have, go over those topics and points that we have made. Okay, I want to believe that information about your coursework or assignment that you are going to submit is going to pass across to you in due time. That clear? So next time we are going to resume from there and run through the remaining elements in the structure of an argument, and any other information that is necessary that I have to give you, I'm going to provide them and pass them to you next week. It's glad to have you there, and please have a great day. Thank you so much. God bless you. Yes, I can come. Thank you.
Sir.
Yes. Yeah. Thank you. Hmm. Good afternoon, class. Good afternoon. Yesterday we were at length equation. Let me send the chat to be sure that good afternoon, class. Am I on? Okay. View. Oh, beautiful. Okay. Okay. So, afternoon, class. So, yesterday we were looking at the length equation, especially for a thin lens, special case of a thin lens, the lens in which the thickest part is thin. I want to believe that's where we stopped yesterday. We're looking at this sample problem at the 4.0, and we are now at looking at length equation. Like I told you, there are many theoretical questions that actually we follow as we go along. And so some of these, theoretical questions in respect of what a lens is, a lens in which the thickest part is thin relative to the object distance P, the image distance I, and the radii of curvature R1 and R2 of the two surfaces of the lens is given by that expression. And of course, we know this is the same as we had for mirrors. But when we look at refractive index of refraction, as it affects lens, then that expression, we try to modify it, in which case we have n, that of the lens, n, that of air, which is 1, and then, of course, the difference between the reciprocal of the refractive indices. This is what we call the lens maker equation. And we know that R1 is the radius of curvature of the lens surface nearer the object, and R2 is that of the other surface. A lens can produce an image of an object only because the lens can bend light rays. And that makes it different from a mirror. For a mirror, being a surface, it's either it will reflect or it will allow the lens, the ray to pass through by way of extension to form an image at the back. But in the case of a lens, there can be refraction. And we know refraction is what? The bending of light rays as it moves from one medium to another. So we are now saying a lens can produce an image of an object only because the lens can bend light rays. And I told you should please note some of these, things. They are very essential because they are the things that can be theoretical in nature. I mean, questions that can be asked. But it can bend light rays only if its refractive index of refraction differs from that of the surrounding medium. But for
the consideration will be looking at is air and then the lens. But in case we have maybe between two lenses, for example, of different index of refraction, that will be different. But for what we are looking at is for lens and the air media. So how do we locate images of extended objects? By ray drawings. Though the figure is not shown, but if you check the text, that's what we call figure 3416A. Or do I have it? Let me see if I have it. Okay, yeah, it's shown in the next slide. Object O outside focal point F1 of the converging lens. We try to locate graphically the image of any off-axis point on such an object, such as the tip of the arrow in Fig 3416. I mean, an arrow can be any object, or just for our theoretical consideration, we look at an arrow. An arrow can be a boy standing. I mean, the head and then to the toe. So, by drawing a ray diagram with any two of the three special rays through the points, that is, any two rays from that object to the lens, should actually help us, any of these two, should actually help us to infer or to actually get the position of the image. So a ray that is parallel to the central axis of the lens will pass through the focal point F2. Let's see that in figure 3416A. Parallel, can you see? Passes through F2. Okay, that's 34A. Ray parallel through the lens through F2. Can you see? So this is the ray, and then this is the refraction after passing through the lens. So it's passing through the focal point F2. That's what that first statement is saying. Then the second point is saying a ray that initially passes through the focal point F1 will emerge from the lens parallel to the central axis. So let's look at ray 2 in figure 3416. Sorry. Okay. Can you see? This is the ray 2 to pass through, and then it's also there. So these two enough can actually show where the image will be. But let's look at 3. Ray 3. So we have looked at ray 1, ray 2. We are now looking at ray 3. Ray 1, this is ray 1. This is ray 2. And this is ray 3. So let's see what ray 3 is saying. A ray that is initially directed towards the center of the lens, will emerge from the lens with no change in its direction. So because the ray encounters the two sides of the lens where they are almost parallel. So with these 2 or 3 rays, you see that exactly we'll be able to locate the image position. These are our objects, and these are our image. So the 3 theoretical considerations, or what we call the rules, actually help us to see how rays passing through the lens actually leads to the formation of image. If you look at B also, the same thing also applies. But in this case, the image is forming right at the back of the object. So you can see first ray parallel to pass through the focus F2. Then the other ray 2, passes through the lens and goes that way. Then ray 3 also passes through the center of the lens. So if you put up an extension of that as if it's at the back, extension of ray 1 also, extension of ray 3 also, the 3 of them actually forms the image here. If you come to figure C also, you see that the first ray it appears to diverge. That's like a divergence. Then comes to F. That is, ray 1, it appears to diverge from F. Then if you look at ray 2, passes, and then it appears to come here also. So depending in the two convex lenses, if the image is beyond F, that's focal point F1, you know, for lenses, we have two focal points. Okay, beyond F1, we can see that the image will be formed here. Between F1 and the lens, the image will be formed here. But if you are talking of a diverging lens, irrespective of the position, actually, the image will be formed there. So the overall or net lateral magnification L of a system of lenses M, of lenses or lenses and a mirror, is the product of the individual lateral magnification as given by equation that. Thus, for two lens system, we have M, they are products. The product of the two individual lateral magnification. That's if you have two objects. So let's look at some problem. A praying mantis, that's an insect, it's nothing special. Preys along the central axis of a thin symmetric lens, 20 centimeters from the lens. The lateral magnification of the mantis provided by the lens is M equals 0.25, and the index of refraction of the lens material is 1.65. 1, you have to determine the type of image produced by the lens. A question like this is very important for you to note and for you to know it very well. We want to determine the type of image produced by the lens. The type of lens, whether the object, in this case, the mantis, never mind whatever the thing is inside or outside the focal point, on which side of the lens the image appears, and whether the image is inverted. These are the things we want to know. So from this question, we know what P is. That's object distance. We do not know the image distance. So we want to look for I in part A above. I will just be 0.25 and then 20. We give us 50 centimeters. So that we can now use the equation now, which is 1 over F, 1 over P. Like I told you, it's still the same thing as what you know before now. But in the case of P, it's now our object, instead of saying 1 over U, or calling it U, call it P. Then V, our image distance is now I. Okay? So by the time we fix that, so the focal length will just be 4 centimeters. It's just 4 centimeters. And if we know that, from our expression that says 1 over F is n minus 1, in bracket, the reciprocal, the difference of the reciprocal of the radius of curvature. So if I put all that, I will actually get the radius of curvature in that expression. And that will give us 5.2 centimeters. So please, a question like this is what you should know. You should know a question like this. It's a very typical question. So you can see that in this slide, we have solved both A and B. You can answer the question here, F being 40 centimeters, being 4 centimeters. Okay? Is it inside or outside the focal point? The position of the object. I mean, the answer is obvious. You can check that out. So, sample problem again. Another one. Some problems are problems you should know very well. Are you hearing me all? Let me see whether you are hearing me. Can you see and hear me? Any of you can actually respond. Can you see and hear and hear me. Just to be sure that we are together. I'm not sure. Hello? I'm trying to get a response from them. It's like they are not even answering from the chat box. They normally answer. Is the volume on? It's on. And the video. Okay. It's okay. Yeah, I just go. Assume they are hearing me. Okay. In the figure, we have a seed placed in front of two symmetrical coaxial lenses, 1 and 2 with focal length f1, being at 24 centimeter, and f2 at 9 centimeter respectively. And in this case, we have lens separation, L to be 10 centimeter. So if the seed is actually 6 centimeter from lens 1, so the question now is, where does the system of two lenses, we have two lenses, produce an image of the seed? So in the first case, if we ignore lens 2, because each of the lenses will produce image actually, okay, each of the lenses will produce its own image. Just like having a lens here, another lens here, and you have an object. The object will have an image, and that image becomes the object for the lens 2. And lens 2 will now have its own image. So to consider the system of lenses, we first ignore lens 2, and we have the image I produced by lens 1. We obtain it so that we have, we use the equation with P as 6 centimeter according to the question, then F1. So we have image 1, which is behind at 8 centimeter. Okay, and it's virtual. So if you look at lens 2, the second lens, we treat I1 as an object for lens 2 now. We call it O2, object 2. For the second lens, I now ignore lens 1. And we can see that this is outside the focal point for lens 2. So the distance P2 between these two lenses, we have it as the thickness and the image, which is 10 plus 8 centimeter. That's at 18 centimeter. And that's what we now use in that equation again. So that the image 2, which is the final image, is plus 18 centimeter. So this suggests that the image I2 is real, inverted, and on the side of lens 2, opposite where the position of image 1, which is now object 2. Yes, object 2. Okay, so we should take note of all this. Please, any question? Do we have any question? Because I'm not sure. Please, any question? Questions, please. Questions? Questions? Okay. So these are the initial consideration we have on this topic. These are the initial consideration we have. And like I told you, if you look at what we have solved, we have defined what we mean by lenses. We have seen how we can draw ray images. And then we've talked about mirror maze. Okay. So let's look at optical instruments. As a first thing, like I told you, this course is about looking at objects in the visible range. For those of us, we still remember our O-level physics. We know that on the EM spectrum, we have the radio, infrared, UV, infrared, visible UV, X-rays, and gamma rays. So we are particularly looking at what obtains in the visible. That's the human eye, visible by the human eye. So the human eye is a remarkably effective organ. And of course, we can extend its range. That is what can be seen if you make use of instruments. As we have eyeglasses, you know, some of us with eye defects, with the right eyeglasses, we can actually see better. Then with microscope, we can see tiny objects, as we have in those doing biology, and say organisms, tiny bacteria and all that. And then, of course, for those of us who want to view distance objects, we can use telescope. So these are the things we can actually use to aid human visibility. So many such devices extend the scope of our vision beyond the visible range. And of course, we have satellite-borne infrared cameras, X-ray microscope, things that can help us to see things beyond the visible range. So simple magnifying glass. So the normal human eye actually can focus a sharp image of an object on the retina, which is at the back of the eye. So if you see our eyes, actually, it's like a lens. Our eyeball, if you check our eyeball, it's like a lens. And so we can use the lens to look at an object, and that object we see with our eyes actually form an image at the back of the eye on a particular portion which we call the retina. If the object is located anywhere from infinity to a certain point, which we call the near point, Pn, the angle theta prime occupied by the virtual image is larger than the largest angle theta that the object alone can occupy and still be seen clearly. So we define what we call angular magnification. If you see the illustration we have in the accompanying figure in this slide, you'll see that in A, because we have A, figure B, figure C, you see that in A, the object is the height of that object, or the tip of the object, is at an angle to the human eye. Can you see? It's at an angle, so that angle theta. But if you are looking at a distance object, still the angle theta prime to bring about this magnification. See the object, see the final image. So the ratio of the angle actually gives what we call angular magnification. So the angular magnification of a simple magnifying lens or simple microscope is a comparison of the angle occupied by the image the lens produces with the angle occupied by the object when the object is moved to the near point of the viewer. So from that figure, if you assume theta is approximately h over 25, and theta prime is just h over f. So we find that if you put theta prime, this will just be 2.5 centimeter, no, 25 centimeter over f. That's the angular magnification of a simple magnifier. Please, let's take note of that. Let's take note of that. That angular magnification, the 25 centimeter is coming from what we call the near point, the far and the near point, okay? So we find that angular magnification is approximately 25 centimeter over f. So we should take note of that. Every of our equation has ready application that we can use to solve any given problem. So let's look at compound microscope. Since we have discussed a simple microscope, let's look at compound microscope, because in compound microscope, we now have two lenses. It's no longer just one. We have two lenses. As you can see in figure 3.4.20, we have two lenses. There's a lens there. There's a lens there. The lens that is near the human eye, we call it the eyepiece. The one that is far away, we call it the objective lens. Then you see, this is the object. The object is very far away. Okay? So in a compound microscope, these two, the objective lens and the eyepiece lens, can be housed. Okay? You won't see them separated this way. It will have been enclosed. It will have been enclosed, but the distance there will have been according to manufacturer specification. There's a distance between the two lenses. So such that if you have an object here, that object forms an image I. And that image now becomes object for this eyepiece. That's what this thing is showing. This image I becomes the object for this eyepiece, and so this image, or now object to the eyepiece, now gives a final image. We can all draw this easily anyway. I hope we can. That is, ray parallel, close, we bend away, will be refracted. Ray that passes through F will be refracted, and two of them join it to form an image. And this image now becomes an object for the eyepiece. And then again, the same thing, object parallel and close appears to be diverged, because you notice that the object now, or image object now, is between the focal point of the eyepiece and the lens. Between the focal point, this is the focal point of the eyepiece, and the lens, so it's somewhere here. So because it's somewhere here, if you check our previous diagram, you see that the image we still want to go ray parallel, and it appear to actually diverge. And the other one, ray parallel, appears to diverge. And then you have the two here. You now have the final image. So you can see that the image is beyond where O is, and it's bigger. That is why those who work in microbiology lab using compound microscope that is just in front of this objective lens, I told you, to have been enclosed by manufacturer, they will now see a bigger object there, a big. It will be inverted, but because what they are trying to look at is actually tiny things, bacteria. Okay, whether it is inverted or upright, it will be immaterial in the case of an organisms the size of microns. When you say micron, 10 to the minus 6. And that's why we call it microbiology. Micron, 10 to the minus 6. So, but with this tiny object, you are able to get a bigger object. A bigger image, sorry. With this tiny object, you are able to get a bigger image. Okay? So in this diagram, you can see this is the object distance, focal length of objects of the eyepiece. So we can write the lateral magnification produced by the objective as image to the object, or S, in this case, over focal length of the object, of the objective lens. So because the image is located just inside the focal point F1 of the eyepiece acts as a simple magnifying glass. Just saying something about this. And an observer sees a final virtual inverted image through it. So that the magnification, in this case, the product of magnification, which is S over the focal length of the objective times 25 centimeter over focal length of the eyepiece. Let's take note of this. Okay? See the angular magnification for a simple microscope or simple magnifier, and see the angular magnification for a compound microscope. I hope you can see that clearly. So please, let's take note of this. Look at what S is in this diagram. What S is, okay? Between the two focal lengths, that's what S is, okay? If you read through here, let's see. The objective produces a real image I of object O just inside the focal point F1 of the eyepiece. Image I then acts as an object to the eyepiece, which produces a virtual final image I that is seen by the observer. The objective has length F objective, that's the objective. The eyepiece has focal length FEY, and S is the tube length. I told you the manufacturer will have enclosed the eyepiece and the objective lens together. So that is what we call the tube length. That will have been determined by the manufacturer. So we are now saying the angular magnification will just be the magnification by the objective and the magnification by the eyepiece. Please take note. So we'll go on to refracting telescope. Refracting telescope. Please, any question? Any question? Any question? Okay. So this now brings us to, we have looked at two optical instruments, or let's say three. We've looked at the human eye. We have looked at a simple microscope. We have looked at a compound microscope and obtained what we call angular magnification. And in both instances, we have to take note of the angular magnification. These are the addition coming up in this our class, different from what we have done before now. So let's go on to refracting telescope. We will now want to see how we can see objects far into the sky. bigger objects. Can we want to arrange our lenses to see bigger objects at far distances? Because in the case of compound and simple microscope, we are trying to look at objects near, within centimeters or at most to us, and we want to see how we can see tiny objects, how they are magnified. That's in the case of simple and compound microscope. But now for telescope, we want to see big objects, bigger objects at fairly distance away. Distance on the order of astronomical units, 10 to the minus 9 or 10 in meters. That is hundreds of millions kilometers away. So the form we describe here is a simple refracting telescope that consists of an objective and an eyepiece. So in this case also, it's two lenses we are using. And one is the objective that you place close to your eyes, and the other one is the objective that will be viewing the distance objects. There are very small telescopes. If you fold, the simple telescope is when you fold your paper. Just fold your paper in a cylindrical shape, and you put a lens one end, you put another lens another end. That's a telescope. That is a telescope. But it depends on the focal length of your lens, depending. The focal length of your lenses will determine the distance to which you are able to see. So there are many special lenses. And of course, there are very big telescopes. I don't know whether you have heard of what we call this South African Large Telescope, the SALT. Very big mountain on, it is mounted on a building. Very big, but can actually be used to see very distant objects. So the lens arrangement for telescope and for microscope are similar, but telescopes are designed to view large objects such as galaxies, stars, and planets at large distances, whereas microscopes are designed for just the opposite purposes. Okay? To view smaller objects, okay, and at small distances. That's the meaning. So, I put that in bold letters for you to actually take note of that. So this difference requires that in telescope, as we see in the next figure, that's a telescope. The second focal point of the objective f2 coincides with the first focal point of the eyepiece f1, whereas a microscope, these points are separated by the tube length s. So we want to define also the angular magnification, theta, of the telescope as ratio of theta of the eyepiece to theta of the objective lens. So we can write theta of the objective lens h prime over the focal length of the object, of the objective lens, and theta for the eyepiece is h prime f, that's the focal length of the eyepiece. So this will give us, if you look at the ratio of the two, this will give us the angular magnification m theta, just to be the ratio, a negative form of that, of the objective focal length to the eyepiece focal length. Please, let's take note of this also. The angular magnification of the telescope is given by the ratio of the objective focal length to the eyepiece focal length. Let's take note. So this is a diagram showing the case of a telescope. You can see there's a lens here that will view that distance object. The object will be far away. You can see the ray coming from a far object. It can be anything. So you have the lens, the objective lens, then you have the eyepiece lens. So from a distance object, the image will be formed somewhere here. The image will be formed somewhere here. And then final image will be formed somewhere here. And you can see, we define what we mean by the angular magnification for each of the lenses. So in A, let's look at what we have here. A thin lens representation of a refracting telescope from rays that are approximately parallel. Any question from question? Any question from you? I can see somebody writing on the charts. Any question before we go ahead? Okay. So a thin lens representation of a refracting telescope and from rays that are approximately parallel when they reach the objective. Okay. The objective produces a real image eye of a distant object of light, of a distant source of light. One end of the object is assumed to lie on the central axis. Okay? Image eye formed at the common focal point. So the image is formed at this common focal point. Okay, you need the next slide for this. Okay? I should hear from you. Yes. Is that the slides you need? You can check it. I can wait for you because if you don't talk, I won't know. It's good to hear from you. Raise your question. It will help in the delivery so that we're on the same page. I won't assume too much so that you'll be able to follow and follow me correctly. So please, like I told you, let's take note of the angular magnification f theta in the case of a telescope. Very important. Okay. I think you are done. So the objective has focal length f objective and the eyepiece has a focal length f eyepiece. So in the B part, we can see in this figure, image I has height h prime and takes up angle theta B, measure from the objective, and angle theta EY, measure from the eyepiece. Okay? Okay, so magnification is only one of the design factors for an astronomical telescope and is indeed easily achieved. So magnification is very important. So for a telescope, in the design of a telescope, we should take note of the following. In the design of a telescope, it must be such that it has a light gathering power. The parameters are the things I put in bold letters. Good telescope must have a light gathering power because this determines how bright the image is. This is important for viewing faint objects, such as distant galaxies, and is accomplished by making the objective diameter as large as possible. Imagine, man's ability to design telescope actually help us to understand the space and the space environment very well. Because with such a telescope, Kepler was able to make observations spanning over a very long time. And because of that, Each time it will locate the position of the stars. You know, he puts a mark, puts a mark, and by the time he was joining all the points together, he was able to realize that really such an heavenly bodies actually describe an elliptical path. Elliptical path. That's not a small main feat at all. It's not a small feat at all. It's something very great. That's actually help us to understand the motion of planets, including our planet Earth. So the next thing is a good telescope also need a good resolving power. A good resolving power. This is the ability to distinguish between two distant objects. There are two distant objects. Your telescope must be such that while trying to look at the two objects, you can focus on one than the other at any given time. So, power to be able to resolve, to focus on one, you know, is very important with a telescope. Because the two objects we want to see may actually be very close in a way. Because as we go further, what happens? You begin to see many objects together, but your ability to resolve, to distinguish is also very important. So the field of view is another factor. It's another important design parameter. Many of these things that we are talking about, those of you that will work in the area of space and space development, you now say, but I was told that time, you know, this will form the basis for you. At least as you go along, there are many of these things are things you know from elementary physics. Okay? And for those of us who wants to work in the lab also, using microscope, once you have microscope, you will not be afraid. These are things you've heard of in physics, and you know the principle behind them. So another parameter is the field of view. So because a telescope designed to look at galaxies, which actually occupies tiny field of view, is much different from one designed to track meteors, okay, which moves over a wide field of view. So the telescope designer must also take into account the differences between real lenses and the ideal thin lenses we have discussed. A real lens with spherical surfaces does not form sharp images. Sharp images, which we call spherical aberration. Also, because of refraction by the two surfaces of a real lens, depends on wavelengths, and a real lens does not focus light of different something. So these are the areas we can cover for today. I don't know whether you have a question. You still get the slide, but not yet. Just try to follow. At the beginning of this class, we have given the reference text. You can do your well a lot of good. You can lay your hand on the reference text. And like I told you, please take time. Take time to look through all that we have discussed today. Take time to look through all that we have discussed today. We started from here, where we have 14 lens, and then 14 lens in air. That's the difference. When you have thin lens, and then thin lens in air. We also gave how we can draw rays, that any of these two rules, if properly applied, actually can help us to draw the image of an object. So these are the application of the rules. Then we have sample problems. I told you, take time, look at the sample problems very well, understand them. And I told you in our last class on Monday, for those who were present, many of you were not available on that Monday. For those who are present, I want you to know that for every 10 questions, about 6, I use the word about, I'm not, it cannot be exact, about 6 of such questions out of 10 will be questions you need to calculate. You'll be given values and then you do small calculations. The remaining 4 or 5 will be questions that are theoretical in nature. Okay? And that is when, like for example, what a thin lens is. Okay? One want to ask that. And which of the following can give rays of a ray can lead to the formation of image? Okay? I can give any of these 2 or any of these 3 or one of them that is not correct. There's a way to set a question on that. And you have a very good question and you have to solve it. Okay? And then optical instruments. We have the simple magnifying lens, or what we call simple microscope. We're able to get an expression for a simple microscope. Okay? What we call the angular magnification. Then for a compound microscope, we also have the angular magnification for a compound microscope. Then we now move on to telescope. You know, I told you microscope can help us to see very tiny objects, smaller masses to the tune of or the order of 10 to the minus 6. That's why we use the word microbiology. Very tiny objects. Therefore, people want to look at something to fast pace. We say we want to use telescope. So you can see the beauty of our good understanding of optics, or how I can arrange lenses to actually observe objects depending on the size of the objects. If they are very small, I can use a simple magnifier, simple microscope. Is something I can also do. I can use a compound microscope. But if I want to see something very big and at large distances, I say, no, let me use a telescope. And of course, we have an expression for angular magnification of a telescope given by what we have here. And then magnification in respect of designing a telescope. There are things that are of importance. The telescopes must have a light gathering power, must have a resolving power. The field of view must be an important factor in the design. So these are the important things. So in our next class, we go on to light as a wave. We have looked at light, as a ray. We'll now be looking at light as a wave in our next class. God willing, by Friday. Thank you very much. So meet on Friday. Thanks. Okay.
Good afternoon, students. My name is Dr. Bruno Igbenegu. The module for today is Module 8. That is Academic Libraries and ICT. Academic Libraries and ICT. It's not moving. Can you touch it? Academic Libraries and ICT. The acronym ICT means Information and Communications Technology. ICT means communication of information through technology. Libraries are undergoing serious and tremendous changes all over the world. These changes are due to advancement in technology. These changes are due to advancement in technology, the ubiquitousness of computers and allied devices, proliferation of the internet. Most libraries run hybrid systems today, although at different levels of ICT deployment. ICT influences library services efficiently and effectively. The main aim of deploying the use of ICT into library is to enhance the most possible efficiency and effectiveness in the rendering of library services. Library management system. Library management system, also known as integrated library system, is an enterprise resource planning system for the library. The library staff employ it to manage the acquisition, cataloging, and inventories of documents. Library patrons use library management system to find, reserve, and loan documents, and manages asset collection, as well as relationship with their members are used by academic libraries as well as public or private libraries. Advantages of ICT in libraries. It has provided new media, new modes of storing and communicating information. It makes many services in the library to be available to library users in a faster way. It removes barrier of communication, distance, and time. The advancement in technology will continue to improve the effectiveness of library services. Catalogs are now available online, called online public access catalogs, free of cost. The available information present in the libraries can be fed to home pages and made available to users anywhere. Qualities of library management system include a database that can be used to store and manage information on different types of content, assets in different formats, manage patron and members information, including profiles, present and past loans, payment, and penalties. It allows users to find information from public sources like OPAC, Online Public Access Catalog, or World Catalog. It manages asset inventory and loans across multiple physical locations. It also provides statistics on loan, inventory, late returns, or lost documents. Library management models include acquisition, that is ordering, receiving, and invoicing materials. Cataloging, that is classification, classifying and indexing materials. Circulation, that is lending materials to patrons and receiving them back. Serials, tracking magazines, journals, and newspaper holding. Online public access catalog, or OPAC, public user interface. Administration and report generation. Examples of library management systems include Follett, Destiny, Intuta, Millennium, Virtual, and so on and so forth. Advantages of library management system include record maintenance, time-effective and cost-efficient, reliable and secure, increased employee efficiency, and simple and easy to use. Electronic information resources / databases. They are those information sources which are accessible only or alternatively through computer access, smartphones, and so on, etc. They can be locally mounted and accessed remotely through the internet. They can be stored in cyberspace and can be accessed simultaneously from different points by several people at the same time. Electronic databases are collection of electronic information sources, that is, e-journals or e-books, by publishers from various fields or disciplines. Some databases are provided free of charge to libraries in developing countries by their publishers or vendors, while others require some fee for subscription. Types of electronic information resources include monographs and course literature, which includes course books, compendium, and students' note. 2, scholarly journals, articles, conference publication, working papers and reports, thesis, that is master's and doctoral thesis. Then the newspaper, that's newspress, popularly known as articles in the newspapers that are not academic. Types of electronic information resources also include GLE literature, company information, official sources, and others. Other sources whose references are not comprehensive enough, or sources that do not fit into the categories described above. For instance, computer programs or codes. Access to information resources and databases. You can access information resources and databases through, number 1, the internet, 2, intranet, 3, CD-ROMs, 4, OPAC, that is online public access catalog, then mobile phones, 6, personal computers, and others. Advantages of electronic information resources. 1, is convenience for accessing articles. 2, timeliness, that you can use it at any time. 3, ability to search the text. 4, animation of graphics. 6, ease of skimming and searching. 7, possibility of downloading or printing the desired document or segment. 8, currency of information. 9, speed of access. 10, ability to send articles to colleagues. 11, storing articles electronically. 12, access to a wider range of information. 13, faster access to information. And 14, easy access to information. All these are advantages of electronic information resources. The disadvantages of electronic information resources include discomfort of reading from the screen or poor graphic quality, time-consuming and distract users from doing their work. 3, lack of information technology knowledge. 4, non-awareness of relevant resources in the collection. 5, information overload. All these are disadvantages of electronic information resources. Institutional repository. Institutional repository consists of formally organized and managed collection of digital content generated by faculty, staff, and students in an institution. They are open access system. The content receives more use from the academic community because it is free. Institutional repository also make it easier for faculty members to get previously scattered or restricted access materials in a single location. Why institutional repository? The reasons for having institutional repository is 1, to promote the principles of open access by providing opportunities for faculty self-archiving. 2, to preserve and disseminate a wide variety of content beyond traditional scholarly articles, including data sets, learning objects, electronic theses and dissertations, audiovisual contents, and presentation. It helps universities fulfill obligation to make publicly funded and non-profit funded research available on an open access basis. It encourages access and sharing among disciplines and institutions. It also allows universities to capture digital e-learning courseware so they can expand on existing programs. It is institutional repository content. 1, published research materials, e.g., book chapters, journal articles, conference papers, and so on. Number 2, unpublished research materials, e.g., preprint, working papers, thesis and dissertation, technical reports, progress status report, committee report, presentation, teaching materials, audio and video clips, etc. Supporting research, then number 3, supporting research materials, e.g., data sheets, models, and blueprints, and so on. All these are the content of repository institutional repository. These are the content of institutional repository. Features of institutional repository include registration of institutional users, that is authors, document submission, approval, moderation, archiving, dissemination, and administration. Digital electronic libraries are libraries in which collections are stored in digital formats and accessible with the use of computers and other allied devices. The content may be stored locally or accessed remotely. It provides academic researchers with electronic access to national and international scholarly journals. Functions of digital electronic libraries include access to large amount of information to users wherever they are and whenever they need it. Access to primary sources of information, support multimedia content along with the text, network accessibility on intranet and internet, provide user-friendly interface, hypertext links for navigation. The functions of digital library continues. Client-server architecture, it provides enhanced advanced search, access, and retrieval of information. It also provides integration with other digital libraries. It reserves unique collection through digitization, and it enables one to perform searches that is not practical manually. Then it also improves and supports library operations. Advantages of digital/electronic libraries are nearly unlimited storage space at a much lower cost, reallocate funds from some staff collection, maintenance, and additional books. It has no physical boundary, and it is round the clock available, and it has multiple access. It has multiple access to electronic libraries. It also enhanced information retrieval and preservation for some print materials. It also have added value and is universally accessible. Limitation of electronic and digital libraries include lack of screening and validation. 2, lack of preservation of fixed copies, in bracket, for record and for duplicating scientific research. 3, lack of preservation of best in class, for difficulty in knowing and locating everything that is available and differentiating valuable from useless information. 5, job loss for traditional publishers and librarians. 6, costs are spread and many become hidden. Library security. Library security. Attendance.
No.
Library security. Arrangements provided for safe and secure facilities for library staff, library resources, equipment, and library users. Libraries should concentrate and implement security policies, procedures, and plans in an effective and efficient manner. Security systems should perform their functions as seamlessly as possible without interfering with the primary objectives of the library. Non-technological approaches to material theft prevention, including guards, physical checks of patrons' packages, closing of stacks and boot bookmarks. Need for library security. 1, theft and mutilation. 2, vandalism. 3, disruptive behavior. 4, damages and disorder and disaster. Damages and disaster. That is natural or man-made disasters. 5, book misshelving. And 6, mutilation by humidity and microbes. Measures against risks in the libraries. Measures against risks in the library. 1, we should have closed circuit television, CCTV. We should have closed circuit television, CCTV. 2, electronic magnetic security system. We should also have ball gas system. We should have radio frequency identification system, biometric systems, access control system, X-ray security machine, and robot security system. Challenges to security breach management. 1, lack of funding. 2, mishandling and late arrival of library collection. 3, inadequate management support and library leadership in tackling security issues of the library. 4, lackadaisical attitude of library staff towards securing the library environment. 5, lending without proper procedure. 6, proper place to keep collections of patrons and professionals. 6, inadequate staff or training workshop on security issues or lack on security issues or systems. 7, lack of user awareness of what constitutes security breaches. Conclusion. In this lecture, we have discussed the importance of ICT to library services. We have also discussed library management system as a tool for modern library operations and why library electronic resources are important to learning. We also discussed institutional repository as a catalyst in projecting the image of an academic institution, digital libraries as a gateway for digital electronic information resources. Library security was also discussed with respect to threats to library resources and solutions to different threats to library security. Thank you. Questions? Do I need to ask you questions? For question number 1, the acronym for ICT. What is the acronym for ICT? Number 2, list all the advantages of ICT. 3, mention all the modules of a library management software. 5, the content that may be included in an institutional repository are: number 5, what are the possible threats to library resources? Thank you very much for your time and for listening to me. We have come to the end of this lecture.